And the recording is started now. Okay, now, guys, what we are going to do today, let's see. What we are going to do today, I'm just going to continue from the things that we did from last week. And if you remember last week, what we did, we talked about eigenvalues and eigenvectors. We talked about let's say, for example, the PCA, and we talked about, for example, the covariance matrix. We saw that, for example, we were able to just define the covariance matrix. We find the eigenvalues and the eigenvectors of the covariance matrix, and we just use the downstream applications of that. Today, we are just going to heading towards the same applications that we had before. We're going to talk about the eigenvectors, the eigenvalues that we talked before. However, today, we are just going to use those concepts for a different thing, which is very similar in terms of the application, and it's a very powerful methods in both math and physics, and also when it comes to machine learning and AI, and that's single value decomposition technique. We're going to talk about that. Again, the ingredient for that is going to be the concepts and understanding of the matrices. And also, we have to again go back to the things which we have been doing since week one, which is the eigenvalues and the eigenvectors, and how we just use the characteristic equation to get the eigenvalues, then migrate towards the eigenvectors computation. This is again the core of what we're going to do today. However, before we just go there, which is going to be the second part of our recording, I'm just going to talk about a very important concept, which if you're just going to have a lectures on that, it takes days and days. You can talk about the applicability of that in quantum mechanics, for example. We are just in many different fields, but in order to talk about single value decomposition technique, we need to know that. Then as a result, I'm just going to spend only 5 minutes to review the concepts that when we are over there, when we talk about that, you know, what does it mean? And the concept is nothing than orthogonality. You see that over there? Orthogonal matrices. You have seen the orthogonality before, let's say, for example, in the previous studies that you have had, but now you're looking into that from a very brief mathematical perspective and 1-2 applications of that, which is so important for the second half of the lectures, which is single value decomposition. Yes, brother? Are you excited to hear about that? Are you sure? 100 is not enough, brother. 110%. Okay. Now, okay. This is the lesson overview. I already talked about that. Now, I'm just going to introduce some basic definition. Then I'm just going to go to the whiteboard to do the calculations over there. Over here, this is blah, 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 blah. But on the whiteboard, this is he, 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 because it's going to be very important on the whiteboard. I have to do the math. Now, we define orthogonal matrices if, for example, we say, imagine, Sonia, you have a question to ask? You have a question? No? We say, imagine that we have a matrix, which we call that A. We say that if we can define this condition with respect, if we can impose that matrix to this definition, then we say that why matrix A is orthogonal. This is a very important thing that we discuss. We say that if you have a matrix A, we can build the transpose of it. You remember last week we talked about the transpose matrix? I said everyone stand up. And when you stand up, I said that you are the matrix. If you lie down on the ground, you become the transpose of yourself. It means that the columns becomes the rows, or the rows becomes the columns. And that's AT means transpose of that matrix. Then you start with the matrix. You transpose the matrix. You find the dot products between them. And if it gets you to I, everyone remembers what was the I? Identity matrix. We said that everywhere, all elements are 0 except the main diagonal, which we had 1. Then, if you can find anywhere, you just go to Tim Hortons, you can find the matrix there. You can impose this definition on that. You call that matrix, this is orthogonal. Okay? Now, we are not gonna talk about and the geometric representation is that we are just gonna see that next week, that if, for example, two vectors essentially are orthogonal, It means that the dot products becomes also, for example, it means that they are normal to each other. You're going to see that next week when we just talk about more about the geometric interpretation when we're just working with the PCA in different directions. You're going to see that geometric representation more next week. However, I'm just going to talk about these four qualities, which I hope you take notes of that for the workshop that you are going to submit. Then I'm just going to solve one problem. Then we finish this part of the lecture. We move on to the single value decomposition, which is the main topic for today. A question? No? Okay. Now, the first thing is that you remember if we talked about that last week, we said that the identity matrix, guys, everyone remember, we talk, for example, if I talk about number four, everyone imagine number four. You can close your eyes. Everyone close your eyes, please. Everyone, take it, lean back, lean back, lean back, everyone. Lean back. Ah, that's great. Close your eyes. Don't be shy. Close your eyes. Lean back, close your eyes. Close your eyes, please. No, not laptop, eyes. Lean back, close your eyes. Uh, yeah, close your eyes. Now, oh my God, why do you not close your eyes? No, I'm kidding. Just imagine a number. Close your eyes. Imagine a number in your head. Imagine a number in your head. Inverse that number. For example, I imagine 4. I inverse it, becomes 1 over 4. Multiply them together. You get 1, exactly. And now wake up. Now wake up. Oh my God, you fall asleep. Oh, wake up. Now, you see, the thing that you did was that you looked at a number, you inversed it, you multiplied that, you got 1. Now imagine this thing. Instead of a number, imagine a matrix. Now, you have a matrix. Instead of the 1 in matrices, we do not have number 1 as a scalar. Instead, we have another matrix, which we call that identity matrix, which just the diagonal is 1. The rest of it is 0. And now look at this one. And imagine this one, that now, instead of a number, that you inversed it, you multiply that, you got 1. Now you have a matrix. You inverse the matrix, you multiply that to its inverse, then you get what? Identity matrix. It's very similar to the dreams that you had. You had a number, you inverse it, multiply that, it got 1. You have a matrix, you inverse it, you multiply, you get identity matrix. It's very similar, huh? Now, but look at the definition that we had over there. We had this definition, we had the matrix multiplied to its transpose, you got I. But from this visualization that you had in your mind, you expect that if the matrix is multiplied to its inverse, the product should get you to the identity matrix. But in this definition that we imposed, we have transpose matrix, which means that the transpose matrix in orthogonality is nothing just the inverse of the matrix, which is the identity 1 which we have there. You see, then as a result, if you go, let's say, to the McDonald's, you can find a matrix there over the counter, and you see that you impose that condition, and that becomes orthogonal, then you know that in orthogonal matrices, their transpose and the inverse, they are the same, because the definition showed that. Huh? Now, the second thing which we are just going to do that when I just go to the whiteboard is that the determinant of an orthogonal matrix is very clear. It's going to be either +1 or it's going to be -1. I'm just going to go back to talk to what is the determinants. We are just going to have an example on the whiteboard before you just go for the break. Then you see that if you have an orthogonal matrix, the determinant is either +1 or -1. This is a very, very important. The other one, which is number 3, which I hope that you take notes of it for the submission, it means that it keeps the orthogonal matrices preserve the norm of the vector if you transpose it. Oh my God, listen, you do not have to be worried that you're sitting at the back. Come here to sit at the front. Come. Come here. Nothing to worry. Come here. Yes. No, no. Yes. And also you. Look at how many space that we have. One of you here, one of you there. Come here. Do not worry. Guys, you see we have enough space. Come here. Now, guys, you do not have to argue on that. Look at how many spaces we have. I knew you two want to come to the seat at the front. Good you mention it. Thank you. Awesome. Great. 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 You see? Everything with open communication, there's a solution for that. You talk to me, you need to come to the front, you come to the front. You see? Easy. Now, the next thing which we done that it's going to be the important part is number 3, which it means that if you have an orthogonal matrix and you have a vector, I'm just going to show that in an example on the whiteboard. If the vector has a norm, you transform that by an orthogonal matrix, the norm of that vector doesn't change. This is the most important thing we can think of orthogonal matrices. We're going to see that in the single value decomposition concepts after the break. This is the most important one. I'm just going to, on the example on the whiteboard, I'm just going to show that to you. But please take notes of it, that when we are there, you see, oh, why that example is there, you understand it. And also, it also preserves number 4 is not that important, but I'm just going to focus on number 3 when we just go there. Number 4, essentially, it says that when you have a dot products between two different vectors, the A transformation on that, as you remember, has no impact on it. And that's the beauty of orthogonal matrices. And I'm just going to finish it by this one on this slide, that whenever in matrices we have orthogonal matrix, is mean that you can transform a vector there. In machine learning, always you're working with the vectors. It means that you can transform a vector with that without changing the magnitude, the norm of that vector. You can transform it. For example, you can transform it to different things. For example, imagine how it works. Guys, imagine yourself as a vector. You are for example, look at yourself. You are a vector, for example. No, I bring the example of myself. I bring the example of myself. Guys, look at that. Imagine me as a vector, and my clothes is a kind of an orthogonal matrix that it transforms in. When I have my clothes, it transforms it to a different look, right? Right? But next week, I'm just going to come, what the t-shirt color which I have today is black. If next week I come to the class, imagine me as a vector, and my clothes, it becomes like an orthogonal matrix, which transforms me. No problem, bless you. And now I'm 6.1 or 6.1 inch height. If I come next week with the blue shirt, do you find me taller or smaller? The same height. Exactly. And if that's the case, it means that my clothes is a orthogonal clothes. It didn't change my nor my length. And that was an example of this one. We're just going to show that on the example that we are just going to have. Okay, there are some examples. We are just going to talk about this one a little bit later. But now I'm just going to stop the share, go to the whiteboard, and solve one very quick thing. Then we go for the break. Then we come back for uh, the single value decomposition. Okay, everyone sees the screen which I have shared. Awesome. Now, look what I'm going to do. Very briefly, I'm just going to show you the orthogonality and the qualities that I discussed about. Then we just go for a break before we just come with the single value decomposition topic. And please, everyone, make sure that the things which I'm going to write, please make sure you take a good brief notes of it. That's the one you submit today, part of the workshop for these 2 folders. Okay, I'm just going to start with this. Sonia, no worries. Look at the space we have there. Come to the front. Come here. Yes, no, you can submit it by week 14, or I recommend by the end of this week. Are you sure you don't want to come over there? Okay. No worries. If you want next time, if I feel that you want, I'm going to ask you to come to the front. Okay. Now, I'm gonna find your friend. Look at that. I'm gonna bring your friend here next to you. You are not gonna be alone. No worries. But before we leave today, you are gonna have lots of friends sitting next to you. No worries. Now, I'm just gonna work with the matrix A. I'm just gonna build a matrix which it comes with these elements there, -1 and 0. Okay, and first of all, you see the ranking of this square matrix. It has 2 rows, 2 columns, which it means that this is a 2 by 2 matrix. Am I right? Now, guys, I feel a little bit happy today. Then I need to do something extra. The extra thing which I do is that I say, oh, what happens if I build a transpose of this matrix? The transpose of this matrix, I remember it becomes, look at the first row. Is it the first row? Am I right? The first row in transpose matrix becomes the first column. Then instead of having a row, 0, 1 becomes 0, 1 at the column, right? What is the second row? 0 becomes what? Second column. Then it becomes -1, 0. And it's very obvious in case if you want to track why it happened, look at this one. Look at, for example, -1. -1 comes with it, I call it a GPS address. Means it comes with an address. Where is that located? It's at the column 1, row 2, huh? I say that if -1, I generalize it as an element A, which means that I do not know what is that. It's at the second row, column 1, right? It is the address of that element inside the matrix. This is, what is row is that? Row 2. What column is that? Column 1. Then as a result, this element, if I call it A, is located just right at the intersection of row 2, column 1. That's why I call it A21. If I want to transpose it, A21 transpose, it means that what I need to do, I come here to take, look at that, 1, replace it with this, and because I know that the column changes to what? To the row changes to columns. And I take 2, I change it to here. Then as a result, if I do this, what do I get? A21 transpose becomes what? A 2 goes to 1, 1 comes to 2. You change the pace. 1, 2. Then it means that transpose of an element which is standing at row 2, column 1, becomes an element at row 1, column 2. Then that's why you see -1 over there comes to where? To here. The element is where? A, which is row 1, column 2. That's how it happened. That's how you transpose a matrix. Okay? Now, I say, okay, I have done all these things so far. Let's go a little bit more crazy. Let's find A, AT. I'm just going to build this product. The matrix itself multiplied to its transpose matrix. I'm going to write them. What is matrix A? This is 0, 1, -1, 0. Transpose matrix is what? 0, 1, -1, 0. Now, I'm just going to find a solution for it. The solution is going to be this matrix. This matrix. First of all, the first thing which I'm going to do, it's a very obvious thing, but I'm just going to do that for the sake of not being lazy. I'm going to first check the multiplication compatibility, which it means that if you remember, this matrix is 2 by 2. This matrix is also 2 by 2. Remember, for the compatibility, this one and this one, they had to match. Then the answer becomes the ones which is left. 2 comes from here, and 2 comes from here, then you see the resulting is going to be also, the resulting matrix of this product is a 2 by 2 matrix. All right. Any complaints? Everyone's happy? Yes? Are you looking for the break? I happy. Good. Now, first one, which I'm going to do. Guys, look at that. This is a 2 by 2 matrix. Means I have 2 rows, 2 columns. Imagine I have, these are the boxes which I'm going to fill it by the numbers. Am I right? The first element in the solution matrix is standing here, which is row 1, column 1. Yes? If this is row 1, column 1, remember from last week, I said the solution of this becomes the output of multiplication of row 1, which I have this one here, times this. Then it becomes this element. 0 times 0 becomes what? 0. 1 times 1 becomes 1. 0 plus 1 becomes 1. Now, the next one. The next element in the solution matrix is located row 1, column 2, which is this one. Correct? This means that then the answer for this is built from product of row 1 times column 2. 0 times minus 1, 0. 1 times 0, 0. 0 plus 0, 10. 0, good. 0 means no one is asleep. Huh? Now, the next thing which I'm going to do is this. This element there, it's second row, first column. Second row is 2, first column is 1. It means that second row is this, huh? Times the first column, 0, 1. That's right. Then it becomes minus 1 times 0. 0 times 0, 1. 0. 0 plus 0, 0. And eventually the very last elements which we have there. Look at this one. This is at column 2, sorry, row 2 and column 2. Obvious? It means that 2 comes from the second row, 2 comes to the second column. Minus 1 times minus 1. 1. 0 times 0. 1 plus 0, 1. Okay? And that's a solution matrix. Then, when I do this, I come to realize something. Oh, very impressive. What is this matrix which I have there? Let me write it there. This is 1, 1, 0, 0. Identity matrix that we had it last week. Because all the elements are 0 except the ones on the diagonal, which we call that identity matrix I. Then what I show, it was that A times its transpose becomes identity matrix. And that's why we see that by accident, that the matrix that we were presented there, it confined to the definition of orthogonal matrix. Then as a result, we get that matrix A is orthogonal, right? Then matrix A is orthogonal. I'm just going to show you two. Any questions so far? Everyone's happy? Have I passed my 20, 25 minutes? It is good. I'm just going to then, if this is good, I'm going to continue with the next half an hour. Let's go on. Now, I need only 5 minutes to show you those two properties from the PowerPoint, then I stop, okay? The first property was what? The first property was that the orthogonal matrices, they have matrices, the determinant is either +1 or -1. Fantastic. I'm just going to show property 1. What was matrix A? It was 0, 1, -1, 0. which we show that this is orthogonal. Now, I expect that the determinant to be what? Everyone remembers. You say, oh, I have some difficulty to remember what is the determinant. I'm just going to come as a note. I have a matrix A, B, C, and D. I say the determinant of this matrix becomes AD minus BC. It's a note from last week. Now, then I come over here. I say, if A, which is shown to be orthogonal, what is the determinant of matrix A? Which means that I multiply this one to this one. 0 times 0 becomes 0. Look at the minus sign there. Minus, I have minus 1 times 1. Minus 1 times 1 becomes minus 1. Minus 1 minus becomes plus 1. Then I have 0 plus 1, which becomes plus 1. Yes. And the first property we discussed over there, it is demonstrated right now there. Then if you have an orthogonal matrix, which is so important as we move along, until week 15, you are going to see orthogonality. Then the first thing which you always remember is that they have determinant either plus 1 or minus 1. The second property was that they do not change the length of a matrix. For example, I'm just going to, for the property 2, I'm just going to go to next page. I'm going to finish it by this one. Matrix A, which is orthogonal, is 0 plus 1. I have minus 1 and 0. This is the same matrix we started today with. Huh? Now, I'm just going to come with a matrix over there. I'm going to define a vector in two-dimensional. For example, the vector, I'm just going to call the vector, for example, a 1 by 2, a 2 by 1. Let's say, for example, 3 and 4. The vector which I have is 3 and 4. Everyone remembers this one, the vector. Cartesian coordinates, you find point 3 on the x-axis, you find the point 4 on the y-axis, you draw a line from the origin to there. Oh, yeah, I got that vector. Huh? However, you remember, if you had a vector like that, I'm just going to show it as a note. If you have a vector comes with nodes, I'm just going to call this vector x. A and B, we remember from maybe elementary school or high school, we set the norm of the vector x. You showed it by this one. Two parallel lines, the vector itself, 2 parallel lines. It means that the norm of the vector, if you remember it from high school, means that the length, for example, the norm of me in terms of the math is 6.1 feet. Remember, it was this one, a squared plus b squared, you take the square root of it. It's from maybe elementary school, huh? Or high school. Now, then as a result, this vector which I had over there, you see that the norm of the vector which I have, it becomes square root of 3 to the power 2, 4 to the power 2, becomes the square root of 9 plus 16, 25, which becomes 5. Now, you see that? Then the norm of the vector, which I'm interested, this is, look at that. Maybe this vector is all that is left for me in the whole world. I'm interested in that. I see that its length is 5 unit. Can be anything, centimeter, feet, foot, anything. Now, I'm going to transform it by this orthogonal matrix. What does it mean? It means that if the matrix is 0, 1, minus 1, 0, it is going to be multiplied to this matrix which I had, which is 3 and 4. And I'm just going to come to see what is going to be the end result. Okay, let's see what happens. Check compatibility. This is 2 by 2 matrix. This is 2 by 1 matrix. In terms of the compatibility, you see that these two numbers match. we take a sigh of relief. So if we can multiply, the end result is going to be what? These things that are left behind, 2 by 1. It means that I have one answer here, one answer here, because 2 row, 1 column. The address of this element there is first row, 1 column. Means that my first row should multiply to the first column here. 0 times 3 becomes how much? 1 times 4 becomes 4. The other elements there comes to the second row, first column. Means that then I have to multiply the second row exactly to the first and only column. Minus 1 times 3. 0 times 4. 0. Minus 3 plus 0. Minus 3. Then it means that the transform matrix which I had, if I call it V prime, is what? 4 and minus 3. You transformed it by multiplying to the matrix, you got this number. As a very final point today, I ask you, what is the norm of the V prime? Which you say, based on definition, 4.2 to the power 2 minus 3 to the power 2 becomes 16 plus 9, 25. And again 5. Look at these two. 5 unit here after transformation and 5 unit here before transformation, which it concludes the demonstration of the second property that orthogonal matrices, if they transform a vector, they do not change the norm and length of that vector in that vector space. Pretty cool, huh? You're going to see more implications of that by the weeks which is going to come. Any questions? Happy, happy, happy? Any complaints? Any advice? Are you happy, happy? Awesome. Thank you. Then, guys, I'm just going to stop the share. We are just going to move on. Next one to the singular value decomposition, which is going to be built on that. Then we are going to take break. Okay. Now, I'm just going to continue with the lesson. As I said, the recording is going to be available on the Google Classroom. In case if you just want to go back, I'm just going to post everything so far in the Google Classroom from today. Now, with the second topic that we have in hand, which we are just taking all the things which we learned from 2 weeks ago, we are just going to again here use the concepts, the core concepts of the PCA that we discussed. I mean by using, let's say, for example, the concept of the eigenvalues, eigenvectors, and we're just going to use the concepts of the orthogonality that we learned at the beginning of the class to come to talk about the singular value decomposition, which is a very powerful technique in linear algebra, applicable to AI like machine learning. And also by next week, we are just going to see the impact of this one in automated drug design when you use the AI for that, for oncology. Now, however, for this part of the course, before we just go through more in details, the second half of the course, it's divided again like the first half in 2 different parts. The first part is very blah, 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 blah from the PowerPoints. Then the second half of the course, which is within 5 minutes, is going to be, I'm just going to go to the whiteboard, give you one example, then you copy paste exactly what to do. You submit it to the workshop folder on the Google Classroom today. Okay? Now, we're going to talk about the singular value decomposition. Okay? We are going to see its significance in drug design next week when we talk about the more relevant applications. However, in order to talk about that, there are, before we just go to see how can we just do the math, the actual math itself, I'm just going to show you 3 slides. These 3 slides, they are the blah, blah, blah part, as I said, the fundamental definitions, before we just go to the whiteboard. First of all, before we talk about, I'm just going to remind you of 2 things. The first thing is that everyone, if you imagine, for example, visualize number 6. You see that the number 6, you can factor this out into 2 numbers, Like for example, 2 and 3, like 1, 2, 3, you multiply all them together, you factorize 6 into these numbers, then you see that the output again becomes 6. The core concepts behind the singular value decomposition is like this one, factorization. Now, we have a matrix. We are going to factorize that into 3 other matrices, which are orthogonal to each other. But the most important thing is that one of them, which contains the singular value, which we're just going to find, captures the most meaningful variations within that huge original matrix that started with. This is the part of the blah, blah, blah. You may, I got bored. You're going to see the actual math in 5 minutes. Then as a result, that's the singular value decomposition. If you see on this shared slide, which I got the photo from the Wikipedia webpage, you see that I started with the matrix M. Look at this on the top. With a matrix M, which the ranking is M times N. No worries, please come in. We see that these matrices, which is M, this is the original matrix, which we are just going to start with it. The ranking is what? We see that it has M rows and N columns. This is M by N matrix. I'm just going to decompose it on the right side. Like, for example, number 6, you decomposed it, you factorize it in 3 and 2, that you multiply them to get the 6. M is factorized into matrix U, sigma, and V transpose. Star is a transpose. You're going to see that. You see that the U matrix is M by M. The sigma, which contains a diagonal matrix, you are going to see that sigma, we call that the matrix, which contains the singular value, which I'm just going to find it at the matrix sigma. And V transpose, which is N by N, you see that it satisfies the compatibility for multiplications. This is the first thing. The second row, what does it mean? That's the thing which we discussed before we come to this class today. Look at this one. One of those factorized matrices, which is U on the top, which is M by M matrix, it is multiplied in the second row to its transpose. Star, it's the T, which I wrote on the previous lecture because I got the picture from Wikipedia. They show that by the star. I couldn't change it. But the star on top of the matrix, it means that that's transpose. It is T actually. Look at this one. U. I not mean you. I mean you here. The U is a matrix multiplied to its transpose. It gets to identity matrix. Interesting. What is that definition for? Orthogonality, which we had before. You remember before the break, we said that if you find a matrix, you get it from McDonald's. You order it from McDonald's. You find its transpose. You multiply them. You see, you get the identity. It means that this is an orthogonal matrix with important properties, that it conserves the norm of the transform matrix and transform vector. Then you see U star, UT, it gives you identity, which it means that U here is orthogonal matrix. The other one, you see vector matrix V also. It is multiplied to its transpose. Again, the same story. You got identity matrix, but square matrix ranking N. You see, identity everywhere is 0 except the main diagonal, which is 1. Then again, you see that the key in singular decomposition, singular value decomposition, SVD technique, which we're going to learn, is that it factorizes a given matrix into 3 matrices that 2 of them are orthogonal matrices. U and V are orthogonal. The one in between, which is sigma, that's going to be a singular value matrix, which we are going to start with this one when we just go to the whiteboard to find it. Now, I'm going to talk about them a little later. With U, sigma, and V, there are some words with that. With the U, they call that left singular vectors. Sigma, they call that singular values matrix, and V, they call it right singular vectors, which we do not need to bother much with these kind of numbers. There is a geometric interpretation. We're going to talk about that next week because you are going to see that we start with 2 rotation and 1 expansion. We're going to talk about that when I just go to the whiteboard. And the truncated one, but this one, which is going to be these things. I hope that you take very small notes of this slide because when I go to the whiteboard, when I'm going to show you this stuff, you need to know this kind of stuff and as a part of the submission that you make. First of all, oh, no, this matrix I just want. This one, please take your notes of this one. I'm just going to explain. Now, after that, I'm just going to go to the whiteboard to solve this one for you. Now, we said that first, we are just going to start with the singular values. When we find the singular values, when I go to the whiteboard, you're just going to observe that the singular values has to always be necessarily a positive or a non-negative value because the singular values, as you're going to see, they are the square root of the eigenvalues that we're just going to find. Then as a result, if you're just going to take the square root of something, then you expect always it to be a positive number. And when you fill out, you're going to see that when I do the real example. When we construct the singular value matrix sigma, when you get the singular values, you just put them from descending order. If you have, for example, 3 numbers, one bigger and one is smaller, you put them on the diagonal on a descending order. You're going to see what I mean. This is very important. The largest singular value corresponds to a direction with more variance. I'm going to talk about that. And the number of non-zero singular values correspond to the rank of the matrix. These 3 things, remember them, take a quick note of it, that when I just go to the whiteboard right now, you do not get confused. But the first part was very important. Now, shall I start the share screen? Okay. Just take a small notes. Just, for example, take the, do not need to write that so much in details. Okay. Shall I stop the screen? I give you half an hour. Good. Try 3 lines. Good. Awesome. What happened to you? You don't want to come to first, sit at the front. I'm disappointed. Now, I just go to the whiteboard. I'm just going to start with the actual math. It's a little bit, it contains a couple of steps. In between of them, we just go for the launch time. Then we come back to the second half, we finish it then. Because it contains lots of steps to take. I recommend you, when I take notes, when it comes to the singular value decomposition, it's important. Brother, why are you not taking notes? Because you have to submit it. No, I know I'm taking notes from there. You show the whiteboard, but I mean, why are you not taking notes? And the funny thing is that he's not taking the notes and sitting just right in front of me. It's good to sit there, but I always recommend to take notes because you have to submit it as a workshop later. Huh? Now, brother, how about you? You copy from him, huh? Okay, then I highly recommend, guys, because it involves lots of notes that we have to take. Everything is in order is so important. Make sure that you have a very good descending way to writing there, step by step. Step number 1, I'm just going to give you the matrix. I'm going to give you the matrix, which is matrix A. And I recommend you do not give your notes to. You have to write it yourself. 4. Oh, yeah, okay. But guys, remember, everyone has to submit his own work. Do not take a picture from one, then send it to everyone. For 3,
You can take picture from one and send it.
It gets 0 then. Okay, now I'm just gonna start. I'm gonna start with this matrix. This matrix which I have is the one like before. For example, before I give you matrix, I said decide if this is orthogonal. I'm not gonna work in that right now. The task is different. I'm just gonna factorize this one based on the singular value decomposition methods that I taught on the PowerPoint. But now we just go in more details. But in order to do so, I have to first come to realize that in order to decompose this matrix, there is a structure for decomposition. I cannot decompose it in any way I want. I know the concepts of orthogonality. I know the matrix A, if decomposed, it comes with 3 terms. The first one is matrix U. The other one, it's a square matrix. It's sigma, as I showed that on that vector. The other one is going to be matrix V, but it becomes a transpose. Sigma here, it's actually, let me write it in less artistic way because I think it was so artistic. Sigma. Okay, I know that if I'm just going to decompose A, which is written on the left side, it has to follow that trend. It has to follow that structure. It's a very rigid structure. As you saw, U and V are orthogonal matrices, but sigma is singular value matrix, which we get the singular value from this. Now, in order to do so, I'm just going to give you the roadmap. The roadmap is this. First of all, the core concepts behind everything which I'm going to do in the singular word decomposition is the concepts of the eigenvalues and eigenvectors. I'm going to use them successively in order to get first singular values, then these orthogonal matrices. Now, in order to start, I'm just going to call that step 1. Step 1 is this. I have to find 2 things. First, you remember we talked about transpose matrix. I'm just going to first, in step number 1, I'm just going to find transpose of my matrix which I have there. The transpose of a 2 by 2 matrix, it becomes a 2 by 2 matrix. I know that the first row becomes the first column. The second row becomes the second column, which becomes 3 minus 5. Look at this one. I'm just going to highlight this fact. Look at this one. Minus 5 that we had over there, it is again minus 5 here. You see, oh, what happened? It's very obvious because this one is at position 2, 2. It's transpose that you change 2 to the row. It becomes 2, 2 becomes 2, 2 itself. Then that's why you see minus 5 at the transpose also remain the same. Now, part of the step 1, which I'm still working, I have to find 2 things. I'm just going to find these 2 matrices, AT and A, and AAT, like the one which we did for orthogonal matrices. This is essentially step number 1. We have to find these 2 products from the given matrix that we have. Now, without further ado, guys, I'm just going to jump in to do these calculations. First, I'm looking to find first this one, ATA. What is AT? I have 4, 0, 3, minus 5. It is 2 by 2. It has to be multiplied to A. A is on top, which is 4. 3, 0, minus 5. Zero minus 5. Okay, now. Okay, the first one that we get, we know that the answer, because it becomes obvious here, we have a 2 by 2 matrix here. We have a 2 by 2 matrix here. The resulting output is what? 2 by 2 exactly. Now, I'm just going to fill out the answers, which comes through that one. The first element, which is going to come through this part, its identity is at first row, first column. Means that the first row multiplies to the first column. Oh, guys, hold on a second. Why it happened? I'm okay. No, that's fine. Now, look at this one. Now, then as a result, what do I have here? I have 4 times 4 becomes how much? 16. 3 times 3 becomes 16 plus 9, 25. How did you made it? Okay, this is the first one. The second element here, the address is what? First row, second column, which it means what? First row multiplies to the second column. 4 times 0, 3 times 5, minus 15. 0 minus 15, minus 15, minus 15. Adita? Now, I go to the third. The address for that is the second row, first column. Now, second row, which is here, first column is this. 0 times 4 becomes how much? Minus 5 times 3. Minus 15, which is becomes this one. And the last element here, which is 2, 22, 2, 2. Second row, this one. 0 times 0, minus 5 times minus 5, 25. Thank you. Then you see that this matrix that I got here, I'm just going to show this one here. AT transpose times A becomes how much? This matrix becomes 25 minus 15 minus 15, 25. Okay, I'm just going to stick it there. Everyone's okay so far? Happy, happy? Now, it was this one, ATA. Now, the next one, remember, I'm just going to find AT. I'm just going to do this. What is A? 4, 3, 0, minus 5. What is transpose matrix? The transpose is this one. 4, 0, 3, minus 5. Then let's see. As before we did, this one is a 2 by 2 matrix. 2 by 2 matrix. We have 2 by 2 matrix as a solution. I'm just going to jump to put the numbers there. Look at the first element. Element is 1, 1. The first row, first column, 4 times 4, 0 times 0, 16 plus 0, 16. This element, which is going to come here, is first row, second column. Means first row, second column here. 4 times 3, 0 times minus 5. Then I get what? 12. Now, this element which comes here, it's the second row, first column. Means the second row here, first column. 3 times 4, minus 5, 0. Add them together, 12. The last element there, this is 2, 2. Second column, second row. 3 times 3, 9. Minus 5 times minus 5, 25. 9 plus 25, 34. Yes. Now, then I'm just going to write it here on top. That A transpose becomes 16, 12, 12, 34. Okay, this is step number 1. Then in order to find singular vowel decomposition, step number 1 is first, from a given matrix, find its transpose, then build these two products, which I did. It becomes number 1. It becomes number 2. Sounds good, everyone? Yes? Okay. I'm going to go to step number 2. For step number 2 is that I'm just going to go back to step number 1, search for A transpose A. Which one was that? It was this one. 25 minus 15 minus 15, 25. I'm going to copy paste it from step number 1, which is A transpose A matrix to over there. Now, what I'm going to do is that at the step number 2, my purpose is that to define the matrix sigma, which, if you remember, it was a matrix that at orthogonal, it had sigma values. By sigma values, I mean, for example, sigma 1, sigma 2, all the way to sigma n, which I know from the discussion that we had on the PowerPoint, I asked you to take a note of it. This step is going to give me this. But in this case, I said that sigma 1 is going to be bigger than sigma 2, bigger than all the way to sigma n, which it was the discussion that I had on that PowerPoint. I said that when you get the singular values, you have to arrange it in the sigma matrix in a descending order at the diagonal. You're going to see what I'm going to do when I find it. But the question that you're going to ask yourself is that you say, okay, step number 2 is going to give me the sigma matrix, but the sigma matrix comes from these singular values. What are those singular values? The singular values is going to be the square root of the eigenvalues of A transpose A. Blah, 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 blah. But you say, too much words. What do you mean? I'm going to say, okay, in order to do that, I look at this one, ATA. I say I'm looking for the eigenvalues of this matrix. But I'm just writing a note here from last week. Remember, the eigenvalue was what? Was A. Let me just not write A, any other matrix. I said that if, for example, if I have a matrix, I'm going to call it M, standing for matrix. If M is multiplied to a matrix X, which it gives me this same vector X, but with a number lambda, the real number lambda, we saw that this is the eigenfunction from last week. Do you remember that? Probably say no. I can't possibly remember that. But this was a definition of the eigenfunction. And lambda here, we call that eigenvalue. Huh? In order to find this, you remember I said I'm just going to take it to the next side. I'm just going to M minus lambda times X goes to 0 matrix. But we saw that because lambda, these are the review from last week, we saw that lambda is a number, M is a matrix. I'm going to introduce identity matrix there in order to make this compatible in terms of the dimension. Then now, we said that from here, we saw that we do not desire the eigenvector x to go to 0. Then we impose this condition that instead the determinant of the m minus lambda I becomes 0. Okay, that's what we did. And by this one, we were able to find the eigenvalues. We called it characteristic equation. I'm going to build the characteristic equation for this one, then we take a quick break, okay? Unless if we don't want to have a break, we can continue. Oh, he got upset. He said he wants a break. Now, look at that. I'm just going to build the eigenvalue only for this one. The structure, I get the eigenvalues when we come back from the break. Look at, imagine that here, what I have, ATA, it represents what M is. They can be the same thing. Then as a result, in order to build the eigenvalues, I'm just going to write this one. I'm just going to write ATA times the vector X becomes lambda X, like the one here. Look at this. I'm going to take it to the other side. I'm going to say AT transpose A minus lambda. I introduce identity matrix over there times X to become a 0 matrix. But we do not want eigenfunction, eigenvector to goes to 0. Then as a result, we said that the determinant of transpose A times A minus lambda I should go to 0. Now, then this one becomes a very... Hello, yes, please, please. Then that's the thing that I'm just going to solve. Now, look at this one. The determinant of this one. Look at this one here. ATA, I have it there. ATA, I have it there. I wrote it there. ATA is 25 minus 15 minus 15, 25. Minus lambda I. What is lambda? We have no idea. But what is I? Identity matrix with the same ranking as the ATA, which is 2 by 2. Then it means that this is 1, 0, 0, 1 becomes what? Becomes 0, but not a number, 0 matrix. I'm going to write it matrix. That's right, 0, but not a number. What does it mean? It means that I'm just going to do the math. I have 25. I have minus 15. I have minus 15. I have 25 minus, I'm just going to take lambda inside, becomes lambda 0, because lambda is going to be multiplied to everything. Then you get a 0 matrix. 2 by 2 matrix, everywhere is 0. I'm just going to simplify that further. I'm just in subtracting. I know that I have to subtract each element of the matrix from its corresponding elements. For example, 25 has to be subtracted from what? Lambda. Because it's 1, 1, this is 1, 1. Everything is subtracting from its corresponding element. Then the result becomes 25 minus lambda. Oh, by the way, the determinant of this has to become, sorry, I just made a boo-boo. The determinant of this has to come to 0. 25 minus lambda, minus 15 minus 0 becomes minus 15. Minus 15 minus 0 becomes 0. 25 minus lambda, the determinant has to become 0. Right? Now, before we just go for the break, let me finish this part. We go there. Remember from the previous course, from the previous break, we said that the determinant of a 2 by 2 matrix, it becomes what? This one. This one multiplied to this one, 25 minus lambda times 25 minus lambda, minus this element times this element, minus 15 times minus 15 becomes 0. That was a definition of a determinant when the matrix is 2 by 2. Now, minus 15 times minus 15 becomes 225. Now, look at that. Minus 50. The first, you have to multiply them. Then you subtract it. Minus 15 times minus 15 becomes 225. This one also, 25 times 25. 625, thank you. 25 minus lambda. Minus again, look at that, this one. Minus 25 lambda again. Plus lambda squared. Minus this one should go to 0. Oh, I just became so much messy back there. I'm going to finish it now in 2 seconds. We go for the break. I'm going to make it everything clean. Then we have lambda squared. Look at this one. I have lambda squared minus 25 lambda minus 25 lambda. How much it becomes? Minus 50 lambda. It means that we have to go for a break, really. Minus 50 lambda. Look at that. 625 minus 225. 400. Equal to 0. Oh. That's the question that we were looking for to find the eigenvalues. We know that the roots to this question gives us the eigenvalues. Guys, do not be worried. Don't be so much excited. Don't be so much. I'm not going to solve it now. I know that you are so much request. I solve it now. I'm not going to do that. I'm going to go for the break. We're going to go for the break. When we come back, I'm just going to start from this equation. Then this equation, I'm just going to have a star next to that, becomes our starting point. Okay. Now, okay, before we just went for the very short coffee break that we had, we just this quadratic equation there, which was the result of the eigenvalues characteristic equation. Now, then you say that what's the purpose of having the quadratic equation? Then the purpose is to solve it, to find two values, because that's a quadratic equation. In this page, I'm just going to rewrite that equation. We had lambda squared minus 50 lambda plus 400 equals to what? Equals to 0. Is what? No. No, still we are on the second step. Still we are there because we didn't finish it because it was too long. Now, look at this one. I take it to the next page. I'm just going to solve it. I'm just going to remind you once again why we are spending these in this very fine evening that we can spend outside to enjoy the nice weather. I'm going to remind you why are we doing this? The point is this one, because we said that we are working with the given matrix A. We are going to decompose it into the product of three matrices. The first matrix, we are just going to call it U, which is orthogonal matrix, as we learned the definition. The sigma, matrix of the singular values, and also another matrix, which is V, which we call it as a transpose. It has a tremendous application in industry, in machine learning, in data science, in physics, in math, which is called singular value decomposition. Why they call that singular value? Because the matrix sigma here, it contains the singular value. Now, you say, what is a singular value? That's a good question. If you're asking it, what is a singular value? That's a very good question. And I'm going to come to say, okay, this is, remember step number one? We just did what? We made two products. A. It was one of the things that we did before we just went for in step number one. Given matrix A, we find the transpose of it. Then we build these products, A transpose A, which you remember we did it on this slide. Look at that, step number one. Look at that ATA. We got it, step number one over there. And that was we did. Okay. Then we said that when we find ATA, which becomes a matrix in step number two, we go to find the eigenvalues of that matrix. How did you find the eigenvalues? It was in step number two. Then I'm going to say that in eigenvalue determination from step number two, we ended up what? With this equation, with this quadratic equation. Now, I'm going to say that if we solve it, we find two roots for it. These two roots, they become the values of sigma. And that's the reason we're just going to find it. Then as a result, when I solve this equation, I'm going to get close to finding the sigma in this decomposition factorization format. Now, how to find this? You remember from elementary school, in order to find the roots of a quadratic equation, I have an equation for that, determinants. It becomes, remember, we had ax squared plus bx plus c becomes 0. We said that in that case, we got x equals to minus b plus or minus square root of b squared minus 4ac divided by 2 times a. If you have been given this equation, remember, I'm going to do the same thing, however, for this equation. Then as a result, lambda becomes, look at b. What is b in this equation? Minus 50. Then minus 50 becomes how much? Plus 50. Plus or minus square root of b squared. 50 minus 50 times minus 50 becomes plus 2500. minus 4. What is A in this equation? 1. 4 times 1 becomes 4. How much is C? 400. 4 times 400 becomes 1600 minus 1600 divided by 2A. A is 1, then we have 2 times 1 becomes 2. Then you see that we get two answers for lambda. For lambda 1, first of all, look at this one here. 2500 minus 1600 becomes 900. 900 square root becomes how much? 30. That's right. Becomes 30. Then we have the lambda 1. Becomes 50 plus 30 divided by 2. 80 divided by 2 becomes how much? 40. It is a lambda 1. Lambda 2, the second eigenvalues becomes what? Becomes with a negative sign now then. I have 50 minus 30 divided by 2, which becomes 20 divided by 2 becomes 10. Fantastic. Now, what did we do? We find the eigenvalues of the A transpose A matrix when we were given the A matrix. Now, based on the theory that we have, I said that the square root of these eigenvalues represents sigma. Look at this. I'm just going to build the sigma. Which one is bigger, lambda 1 or lambda 2? Lambda 1. Then as a result, I start with that one. Then I'm going to say sigma. Look at this sigma matrix here. Then I'm going to say sigma becomes this diagonal matrix, which on the main diagonal, there are just going to be these value. The other places is going to be 0. Look at that. I have 2 by 2. I have 4 possible elements in the sigma because my original matrix was 2 by 2. My sigma is also 2 by 2. Now, the first one, I know that it has to be a diagonal matrix. It means that the sigma, everywhere I have it 0, except the main diagonal. The first diagonal, what is my first eigenvalue, which is bigger than the one, which is 40, huh? Then the first singular value becomes the square root of my first eigenvalue, then becomes the square root of 40. And this one becomes the square root of the other one, which is a smaller 10. You see, I started with the bigger eigenvalue on the top. Then now you see that in order, and normally with the importance of finding the value decomposition matrices is just to find the singular matrix, which is going to be as this. Then in order to find the singular values, what we need to do is that when we are given a matrix, so yeah, and it's not to argue that you want to come to the problem. Tell me there is no argue. You see, she was dreaming to come to the front desk. Please come here. There is no need to dream about it. You see? Look at Sinia. For everything, there is a solution. There is no need to dream about anything. You want to come to the front desk? Come to the front. No need to dream about this. You see, everything is possible. Now, okay, now, let's get back to work. Now, let's get, huh? You did what? Why? Because you were dreaming to come to the front desk? You need to talk only. You need to talk. Now, then we got the sigma. Now, what we did here is the sigma that we find. The next step is that then as a result, let me just recap. We got a little bit distracted. Then in order to find the sigma matrix, the eigenvalues that you find, you have to square root of it. Adita, don't let these people, your friends, alone. Come to the front. Now, then we just got the sigma value over there. Now, the next step is that, look at that. Yes, please, no worries. Don't be shy. No, go over there, over there. Now, yes, good. Now, first, we got this one. Does it feel blurred? Does it feel blurred? Yes, you see, you have such a huge space around yourself. No. Okay, which step was this? Step number, oh, this one was step number 3. This one was step number 3, which we got the sigma from number step 2, which we built. Look at that. Step number 2 was this one, the eigenvalue that we find from the ATA. Step number 3 was forming the sigma matrix, which comes with the square root of the eigenvalues of the step number 2 that we find. Now, then guys, you're asking 2 questions. For example, Adita wants to ask this question. He wants to ask me, but he's a little bit shy. He wants to ask, okay, I remember we talked about when we have the eigenvalues, always eigenvalues comes with the eigenvectors. You got the eigenvalues. Where is the eigenvectors? That's a good question. Thank you. Thanks for asking that. Thank you. Then we just go to step number 4. Based on what Adita proposed, we go to step number 4. Step number 4, we said that in order to find the eigenvectors for ATA, I'm not going to solve everything there. I'm just going to give some kind of a clues there. Then you can continue with that, because the main purpose that we had for this part of the lecture, which I needed for the next one, the emphasis is on finding the singular values, which shows the highest variations. These ones, the eigenvectors, they are just going to be transforming the data along this direction. Then I'm not going to solve everything at this stage. I'm just going to give a kind of a reminder. You can do it at home if you want, but I'm going to take the singular value from today for the next week. Then the thing which I'm going to do here is that because before you, Adita, Sonia was asking. She was asking when she was taking a nap over there. She was asking, you got the sigma. What happens to V and U, these matrices? Us, we decide on the sigma, U and V. We do not care. We have to care, but for this purpose of the class, we do not care to find it. But when Adita asked, what is the eigenvectors? I'm just going to do the eigenvectors, what I do. I say that AT and T, we just A transpose A, we build it. Now, what I'm going to do is find the eigenvectors for that, because the eigenvalues were the square root of 40 and 10. Remember on the previous slide, eigenvalues 40 and 10. Now from those eigenvalues, I'm just going to find the corresponding eigenvectors. How to find it? Remember before. Remember on that slide, we had ATA times X becomes lambda X. We said that ATA minus lambda identity matrix times X should give you what? If you take everything to the other side, it gives you the 0 matrix. I'm going to write it here, matrix. Now, what I'm going to do, I'm just going to solve this equation in order to find the eigenvectors. Look at this one. Now, I'm just going to put everything there. AT and A, what was the matrix that we built? It was 25, minus 15, minus 15, 25. Do you remember it was step number 1? They built this matrix. I have minus lambda I, okay? But remember, we find the lambda. How much were the lambda we find? 40 and 10. I'm just going to use one of them for the first eigenvectors. I'm going to say 40 and the matrix I. Guys, I feel a little bit bad. You two are looking at me directly and I feel a little bit nervous. I feel myself under two heavy eyes looking at me. I was sweating. Oh, I was saying, why people are looking at me like that? Adita, Sonia, please take a note. They were not even blinking. They were looking at me like angry. Stop it. Stop it. Oh my God, I was sweating. Adita and Sonia, please take notes that rather than looking at me. Okay. Now, I have 40. The identity matrix is what? 1, 1, 0, 0. Gives me what? Yes. Yes. Good point. I forgot to add it. X gives me what? Matrix 0. You're going to see how it's that going to be. That's good. Thank you. Thanks. Now, look at this one. This part, I'm just going to come to write it from there. 25 minus 40 becomes how much? Why am I doing this? 25 minus 40 times 1. 25 minus 40 becomes minus 15. Minus 15 minus 40 times 0 becomes 0. Minus 15 minus 0 becomes minus 15. Minus 15 times 0, minus 15. Minus 40 times 1, minus 40. 25 minus 40, minus 15. That's the result. This one is the result there. This is a 2 by 2 matrix. The vector x, which I have there, because it's part of the eigenvector, it has to be compatible. Then I can build it as a 2-row vectors by 1 column. Then as a result, the ending result is going to be what? 2 by 1 also, a vector itself. I do not know. I know that the resulting matrix is going to be a 0 matrix. Then as a result, each element has to be 0. Then I have here x1 and x2, because if you remember from last week, the eigenvectors, we have no idea what are the elements. Then we just put them x1 and x2. In order to find it, look at this one. The solution here, element is 1 and 1. It's the result of multiplication of row number 1 to first column. Means minus 15 x1 minus 15 x2 becomes 0. This one is the second row, first column. The same thing, minus 15 x1 minus 15 x2 becomes 0. This system of the equation. Now, you take a look deeper inside this equation, you see that both of these equations are the same. Then I'm just going to select only one of them, which it means that x1 has to be necessarily equal to x2. You divide both sides by 15. Then as a result, if the eigenvalue is equal to 40, x1 and x2 have to be the same. Then x, this one which I had over there, becomes, I put 1, 1, with the number, I'm just going to call that P. P can be any real number. It means that x1 and x2, they are equal. If P becomes 2, then the eigenvectors is 2 and 2. This is for the eigenvector when the eigenvalue is 40. Now, for the last part before we finish today, this is the last part and we're done. I also remember we had another eigenvalue. Another eigenvalue was what? 10. I'm going to build the same thing for the eigenvalue if this is 10. What did he had there? Characteristic equation, it says that ATA minus lambda I times the eigenvector gives me the zero matrix. Now, the eigenvalue is now 10. ATA, we got it before. It was 25 minus 15 minus 15, 25. The eigenvalue is 10 times 1001. Everything multiplies to x, becomes zero matrix. Thank you. Now, this part becomes so easy. This one, I'm just going to add 25 minus 10 minus 15 minus 0 minus 15 minus 0 25 minus 10 plus 15, you mean plus 15. This is the result of it. This is the result of this one, which is a 2 by 2 matrix. Look at the x which I have there. I'm just going to incorporate the x. I'm going to build it a 2 by 1 vector, means that I have x1 and x2. The end result, the zero matrix becomes 0, but by the ranking of the 2 by 1, because these two are compatible, then 2 here and 1 here builds this one. Then now, what happens here? I'm just going to build this system corresponding to this. I know this one, which is here, this is at the position 1, 1, means first row, first column, that it got 0 over here, means 15x1 minus 15x2 becomes 0. This one also, second row, that's right, becomes minus 15x1 plus 15x2 becomes 0. Now, you see, you can pick any equation you want. I'm just going to pick, for example, this, because they are essentially the same equation. Then you see that if you take x1 to the other side, divide by 15, you get x1 equals to x2. Again here, let me see, I get a little bit suspicious what we did before. Uh-oh. Look at this one. I made a little bit bad mistake. For this one, we had minus 15x1, minus 15x2 with the eigenvalues of 14. It means that you take x1 here, minus x1 equals to x2. I forgot to put the minus there. Because look at that. You divide both sides by 15, minus x1, minus x2 equals to 0. You take x2 to the other side, minus x1 equals to x2, which it means that I had to put a negative there, then I have to put a negative either there or there. It doesn't make a difference. But here, I have this one. That's right, which means that the eigenvector here, it becomes any number, 1, 1 times again P. P can be any real number. Now, the final point before we say goodbye today. Look at this. With the eigenvalue corresponding to This is actually step number whatever. Okay. It's now, this is the final point I'm just going to make, then we are going to be done. Now, what did we do today? At the last step, I'm just going to catch up with the last step. With the ATA, guys, please everyone listen. This is the most important part that I'm just going to wrap it up in a minute. With the A transpose A that I did, I find two eigenvalues and two eigenvectors. The square root of each eigenvalues represented what? The singular value, sigma matrix. The eigenvectors which I built from it, what are they for? Look at that one eigenvector was, imagine, -1 and 1. One eigenvector was 1 and 1, if p is equal to 1, for example, corresponding to this product. Then what do I do is this. I say, remember this, I said A is going to be transposed into U sigma V transpose. Yeah, I think I'm almost done. Okay, V transpose. The eigenvectors corresponding to, the eigenvectors corresponding to A transpose A represents the V. Then what is the V? Is going to be x1 and x2 if you put everything together, -1, 1, and 1. And that's how I built this one. Then this transpose, I keep it there. Sigma, I had the square root of 40, 0, 0, square root of 10. I have the matrix A equal, but the question is that, how about U? Huh? Sorry, what? I didn't mean you. I mean you here. Oh, okay. Now, this U which I have here, I'm not going to solve it, but all the things which I did so far, I said that the eigenvectors, everyone look at this, please take a note of that for your workshop when you submit it. The U is the eigenvectors of the A transpose. Look at that. The eigenvectors of A transpose A gave me the V. The eigenvectors of A transpose give me the U, which I not need to find it. You know how to proceed, how to find the eigenvalues, how to find the eigenvectors, how to put them together and do this one. Then if you do that, I'm not going to do this because the session becomes very long then. I'm not going to do that unless if you want. Brother, don't ask me to do that. I know that you are so excited for it. No, at the back. Anmol, you wanted me to do that? Look at it. No, I'm not going to do that. You are asking me to do that. I'm not going to do that. It takes so much time. No, it takes so much time. I'm not going to do that. I'm just going to wrap the session right now. Then what did we did so far? I'm just going to recap it once. Then before we finish in 30 seconds. Then what did we do? We are just going to work with that next week with the decomposition metrics that we did. Then I just started with two eigenvectors, okay? I just started with a given matrix. I was able to decompose that and factorize it into three other matrices. Two of them were orthogonal. The middle one, which was sigma, it contained singular values. The singular values were the square root of the eigenvalues of the A transpose A. A was a given matrix. Next week, when we come back to the class, we are just going to continue with the significance of these concepts and also the significance of the singular values, which capture the highest variations of the given data sets that we had. Okay? But at this stage, we learned how to factorize it. We learned the square root of, as a last point, the square root of the eigenvalues of A transpose A gives me the singular values. The eigenvectors of A transpose A gives you the matrix V. The eigenvectors of A transpose give me the matrix U, which all of them are orthogonal. And that's for all today. Happy? Any questions? Any complaints? Any feedback? Any anger? No.